again for having me out here. It's been a really nice visit so far. So what I'm going to be talking about today is some acoustic measurements that we're doing in our research group, looking at sediment transport over sandy beds. So this is work that I'm doing at Dalhousie University in collaboration with a bunch of the folks that are listed there. And we also have a group connected with us at Memorial University in Newfoundland. So the experimental work that I'm going to talk about today combined a whole bunch of great people together, and I think we got some really cool results. The basic goal of this work is to apply acoustic methods to measure small scales of sediment transport. So we're looking at boundary layer flow and mobilization of sediment in the boundary layer. And to do that, our group has developed an instrument called the MF-DOP, which is a multi-frequency coherent Doppler profiler. So I'm going to talk about the design and how the MF-DOP makes measurements, and then I'll move to some results from an experiment we did earlier this year where we looked at applying this instrument to a river flume environment, looking at sand in the boundary layer. And so I thought I'd start just with a bit of background motivation. As Joe said, I'm interested in nearshore processes and modeling in the nearshore. And one of the applications of nearshore models is to understand coastal change, so coastal erosion and accretion. But a big challenge to applying models in this area is the broad range of scales that are involved. And so we're looking at acoustic measurements at the smallest possible scale at the interface between the water and the sand. But most models don't resolve those scales, so the bigger picture of making these measurements is to try and develop new parameterizations for the larger scale models. And one of my interests is actually looking at the statistical parameterization of small-scale processes and how that feeds up to uncertainty in predicting the larger system. But today I'm just going to be talking about the observational aspect, which in and of itself is also a challenge. So it's difficult to observe these small scales, and there's a couple of reasons for that, so I've tried to highlight those here. One reason that suspended transport under waves and turbulent flows is difficult is that it's a really intermittent process. So you get these plumes of sediment, like in the photo here, down there, which occur every so often but inject a lot of sediment into the water. So you need an instrument that can resolve in time in order to capture these events. And then another aspect of this process is that it's really concentrated in a thin layer near the seafloor. So there's a huge spatial gradient of sediment suspension in this really small zone. So for a long time, people have been interested in applying acoustics to this problem, and so there's a few reasons for doing that. One is that acoustics can give you measurements not only of what sediment is in the water, but how fast it's moving. So we can look at sediment flux in a coincident type of measurement. Another reason is that acoustics gives you the ability to do this sort of remotely, so you're not influencing the flow itself, you're measuring from a distance away. And then also, using acoustics, there's a potential to resolve the scales of these plume events and the vertical scales within the boundary layer. So people are pushing more and more resolution out of acoustic instruments to try and get at the smallest possible scale. And that's been going on for a few decades now, and most recently, the recent generations of acoustic instruments are these coherent Doppler profilers, which give better resolution than before, both in space and in time, so we can really look at the turbulent flow. So our group is one of just a few that have developed one of these instruments. It's called the MF-DOP. So it was designed and developed in our lab, and it stands for Multi-Frequency Coherent Doppler Profiler. So this is a picture of the MF-DOP up in the corner as it was deployed in one of our field experiments. So it's designed to be deployed in the field under breaking waves. It's a nice rugged instrument. And the way it's deployed is generally we put up a frame in the nearshore. This frame happened to be at about the mid-tide level, so later on it was covered in water. And the instrument itself is mounted about a meter above the seabed, and it makes a profile of velocity, size, and sediment concentration on millimeter scales with tens of hertz resolution and time and all the way down to the seabed, so boundary layer processes. The reason that we're able to get down towards the seabed is because of this bistatic geometry, where we have a center transducer, which is a transmit and receive, and the outboard transducers, and there are 4 of them, are angled inwards, and they're receive only. So the profile is directly beneath the instrument, and then these different transducers look at different angles of phase shifts to measure 3-component velocities. It's a multi-frequency instrument, so we use a software-defined radio system for data acquisition and for transmitting, and that gives a lot of flexibility in the types of acoustic signals we can send out. So we're currently set up to do up to 4 simultaneous acoustic frequencies in the bandwidth of 1 to 2 megahertz or so. And I'll talk a little bit later on how you can use that multi-frequency information to look at the properties of the sediments. And then turbulence resolving, so the range bins can be set to less than 1 millimeter. In the field, we typically use like 5 or 10 millimeter range bins. So now in the next few slides, just for people that aren't familiar, I thought I'd just go through the basics of how the MFDOP actually makes the measurements, so the basic pulse coherent kind of processing. So the idea is to send out a short acoustic pulse from our transmitter. It's like a few wavelengths long or a few millimeters in length. And then that pulse transmits downrange, and interacts with particles along the way, and those particles then scatter back sound, which is received at the 4 different receivers. And the reason that the thing that makes it a coherent instrument is that we measure not only the amplitude of the backscattered sound, but also its phase. And by measuring phase, then you can get a measurement of the velocity of the scatterers. So by transmitting a series of these pulses and then looking at the phase versus time, if you consider that the scatterers or the sand particles are moving coherently within a range bin, then that's going to cause a small phase shift. And by detecting those phase shifts, you can then back out measurements of velocity in the beam directions and then convert that to 3D velocities. My work with the MFDOP is actually more to do with the amplitude part of the signal, and that's how we can look at the properties of the scatterers themselves, namely how many scatters there are in a range bin and what is their size. So for that, the model that's almost always used is assuming a dilute suspension of solid elastic spherical scatterers. So we just model the sand grains as little spheres distributed throughout the range bin. And with a few assumptions, you can then write out an incoherent scattering model that's shown here. And the main assumption here is that we don't have too large a suspension so that there's multiple scattering effects. But with that, so I'll just go through the different terms in the equation here. This is what we measure, which is the root mean square backscatter over an ensemble of pings. And on the right, this is an instrument sensitivity coefficient. So I've done work in the lab to calibrate our instrument for absolute backscatter amplitude. There's an inverse range dependence, so that accounts for spreading of the acoustic energy with range. There's the backscatter form factor and an attenuation, scattering attenuation. These require calibration on a site-by-site basis because they depend on the roughness of the scatterers and the material that the scatterers are made out of. But these are generally calibrated for in the lab as a post-processing step. And then we have what we're really after, which is the mass concentration of sediments M and the particle radius A. And these are then cast as a function of range and time. So the inversion problem is to take backscatter amplitude measurements and back out these 2 parameters. The trick is that since we have 2 parameters in one equation, we can also take advantage of the frequency dependence of the equation. So this is where having a multi-frequency instrument like the MFDOP is useful because we can look at natural flows which have variability in the grain size and invert for that, as well as the concentration of particles. Okay, so as I said, my work has been focused on this backscatter inversion part of the MF-dot processing. One of the difficulties of using the method that I just described with the pulse coherent instrument is what we're after is really high resolution measurements. And when you get to that high resolution, you start to get into statistical properties of the measurement itself, which can cause the inversion to be more difficult. So I'll just briefly describe some lab experiments that I did where I developed some new inversion methods to really do the backscatter inversion at turbulent length and time scales. So in these experiments, we have a tank in our lab, which we call the jet tank, because it has a turbulent jet in it. And so we load up this jet with mixtures of sand and water, and then we fire that into the tank at about 50 centimeters per second, so we get this turbulent cone. And then we set up the MF-dot looking sideways through the jet and make measurements in time. So here's an example of backscatter amplitude as a function of range from the MF-dot, where the center of the jet is 55 centimeters range, and time for 2 minutes of data collection. So obviously the center of the jet is where most of the sand is, and that's where most of the backscatter amplitude is. And then as you get out to the shoulders of the jet, you can see there's a lot of turbulent structure in this setup. So we get plumes of sediment that are ejected out from the core, and also fresh water that's entrained back in. So as I said, I did a series of experiments with this setup where we used natural beach sand with known diameters, and we put in different amounts of sand into the system and then tried to invert for the sand concentration and size. So we got up to 10 grams per liter sediment concentrations, which is roughly the limit of single scattering assumption. And here's some of those results. So this is acoustic inversion of sediment concentration as a function of range from the transducer. Again, the concentration is maximum in the center of the jet, and then we get this nice Gaussian distribution. So the solid lines are the inverted concentrations. And then the symbols are direct measurements using a suction sampler. So this sort of validated the backscatter inversion, and we were able to extend that into the turbulent time resolved measurement. And then finally, of course, we can combine this with the velocity measurement. So this is sort of a cartoon figure. I'm sorry, it's a little bit blurry. But this is showing the sort of the same pictures as before for a few seconds of data collection, where the background colors are sediment mass concentration in grams per liter. And the arrows, which you can barely see, are the turbulent velocity field. So if you look carefully, you can see some really fine coherent structure that we're picking up in the jet turbulence. And you can start to think of how that correlates with aspects of the sediment flux. So after having that validation in the lab, next we wanted to take the MF-dot to more of a field-like setting. So for the rest of the talk, I'm going to be describing some experimental results. We did a month-long field experiment earlier this year in the St. Anthony Falls lab in Minnesota, using their main channel flume. So this is a picture of the main channel flume. It's pretty big. It's 2.75 meters wide. We ran it with a meter deep water column, and we had a 50 centimeter thick layer of natural sand on the bottom of the flume with median grain size of 400 microns. A nice thing about this flume, and actually the whole St. Anthony Falls facility, is it's designed around the idea of diverting water from the Mississippi River and using that in their experiments. So we have sort of an infinite supply of water to run through the flume, and there's weirs at either end to control the discharge rate. And then another nice feature of this flume is the recirc system. So just behind where this photo is taken, there's a gap in the floor of the flume where the sediment gets collected and then pumped back up to the top of the flume. So you can run the flume indefinitely and look at equilibrium bed states and things of that nature. So I'm going to talk about a subset of the instruments that we installed. We brought a whole bunch of acoustic and direct instrumentation. Our main instrumentation was on a fixed frame that was 55 meters from the head of the flume. And that's where we had, of course, the MF-dot, which was roughly 80 to 90 centimeters above the bed level, depending on where the bed was at any given time. And we set it up to profile through the bed and then 30 to 50 centimeters above the bed. We also had a rotary pencil beam sonar, or a ripple scanner, if you will, So this gives profiles of bed elevation directly beneath the MF-DOP in the streamwise direction over a swath of like a couple of meters. So in that way, since the MF-DOP is just a single vertical beam, we could get sort of the broader picture of where it was measuring. And then for the even bigger picture of the bed forms, we used a cart sonar. So this is a mobile computerized cart. It's part of the main channel facility. They have this wing which gets dipped into the water, and then there's a single sonar beam coming out of the wing which measures the bed elevation. So in that way you can move the cart around and scan the bed. So I'll show a few results using the cart sonar, and that was just upstream of our instrument frame. And then finally there's the waypan system. So I mentioned the recirc setup that they have. This is the gap in the flume where the sand gets collected, and along the way they have weight scales so you can tell what the total bed load transport is versus time. So what I think was nice about this experiment is getting back to the idea of the multi-scale nature of sediment transport. In this lab setting, we can look at all the different scales together, going from what I would call the morphodynamic scale, how the bed responds to the overall flow, and then moving down to the bed form scale, where the flow is responding to different bed forms, ripples or dunes, and then down into the boundary layer, and finally the sediment-water interface. And so combining the MF-DOP with some of the flume instrumentation, we're able to sample all of these scales simultaneously. So for the rest of the results, I'm going to try and kind of walk through down this scale. So starting at the largest scale and then moving all the way to individual grains of sand almost. The way we looked at the largest scale was to run the flume with different equilibrium bed states at different flow rates. So we started off by roughly flattening the bed, and then we ran a series of flow rates until we started to see bed forms developing. So these are results from the cart sonar, so just upstream of the instrument frame over 15 meters, just scanning through the center of the flume along stream. So you can see as we get to 1,500 liters per second flow, which I think was about 30 centimeters per second free stream velocity, that's when bed forms began to develop. And then we would run the flume until we saw with the cart sonar that the bed forms were in equilibrium. And once that occurred, we would run the fixed instruments on our frame for a period of time so that we sampled the migration of one bed form past the frame. So in that way, the fixed instruments would see different locations along one bed form. And then, of course, we went to higher and higher flow rates, and so that at the maximum flow we used, which was about 1 meter per second of free stream velocity, we had sand dunes that were 1 or 2 meters in wavelength and about 20 centimeters height. Just a couple of statistics that we looked at to determine that we had equilibrium bed forms. We saw that the geometry of the bed forms increased linearly with flow rate. So we saw linear increases in the height, wavelength, and migration speed of the bed forms. And we also saw that at each flow rate, we had an aspect ratio of about 1:15, and that's consistent with known equilibrium shapes for unidirectional flow dunes. So again, moving on with the large-scale measurements, one of the things that we can look at is the total transport of sand through the flume as a function of discharge. So these are measurements from the weigh pans, looking at the integrated bed load flux. So remember, at about 1,500 liters per second discharge, that's when we started to see ripples, and that's about when the weigh pans were able to detect bed load. And then beyond that, you can see this nice cubic dependence of the bed load with discharge. So consistent with the sort of an energetics perspective on sediment transport. Aside from the bed load, we can also use the MF-DOP with the backscatter inversion to look at the suspended load versus discharge. So this plot is showing the vertically integrated suspended sediment concentration as a function of flow rate. Again, of course, this increases, in this case, linearly with discharge. But what's more interesting is the increase in spread of discharge, of suspended sediment as you go up in the flow rate. And this is really the effect of bed forms. So each of these symbols represents 100 seconds of data collection, where we're looking at really just one point with respect to the bed form. And as you'll see, the bed forms really dominate the signal as you get to larger and larger scales. So they tend to generate a lot of variability in the suspended load. And that's sort of the next stage of this little tour, if you will. So we're going now to the bed form scale. And for this, I'm going to focus in on just one of the flow rates that we used, where we had a fairly high rate of flow, 80 centimeters per second, and we developed dunes in this case. So about a meter and a half wavelength, and about 10 centimeters tall, as you can see. So these measurements on the right are from the pencil beam sonar, which is right underneath the MF dot. The dunes typically had lee faces, so the flow is from left to right here. The steep lee face, about 25 degrees, and the Stoss face was about 5 degrees. And you can also, just as an aside, you can see the little ripples on top of the dunes. So we actually had sort of two scales of bed forms going on here. Remember, the strategy was to collect data over one bed form migration, so that's what this stack is showing. So we started over the Stoss face of one dune, and then over time, the MF dot location migrated to the Stoss face of the next dune. And the data collection strategy was that for each of these pencil beam profiles, we would collect 3 bursts of 100 seconds of MF dot data. So that's what I'm going to be showing over the next few slides. Okay, so each of these profiles is 100 seconds of MF dot data, time averaged. I should probably just walk through how these are organized. So I'm plotting here the profiles versus range from the MF dot, and they're truncated at the location of the bed. The faint black lines are actually the bed location versus time. So you can see in some cases there was a somewhat significant migration of the bed even within that 100 seconds of data collection. And then to average the profiles, the data was translated into a fixed bed coordinate frame and then averaged in time. And that's the profile data that's shown here.
What was the wiggle shape referred to?
The wiggle shape.
So you have vertical axes along all those color strips,